Yeah, so that is working good. Thanks. So good afternoon, and thanks for having me here. I would like to talk today a little bit about our journey to scale down nuclear magnetic resonance to the nanoscale level and about the research done at ETH in Zürich. So our group is generally interested in developing new methods to spatially recognize magnetic features at the nanoscale level, and this includes, besides scanning approaches, also the use of stationary NV centers to do spectroscopy of objects which are close by. And this is in particular, for example, nuclear spins. And as NV centers played already a rather big role in that summer school, I don't want to go too much into the detail of the basics, and just like remind you quickly why we are interested. And this is basically to do spectroscopy of biomolecules which are sitting on top of the diamond. And the idea is, well, if we can infer the position relative to the NV center of these external nuclei, then we can actually image that external molecule. However, although there is a lot of progress towards that direction, this is a really tough goal. And we are not yet quite there, especially the surface chemistry can be particularly challenging. I'll come to that in the second half of my talk. But luckily, we have a toy model at the moment ready, and that are the carbon-13 spins, which are naturally abundant in diamond host lattice. 1% of the natural abundant carbon atoms are carbon-13, and those have a nuclear spin of 1/2. And by that, we can already start today developing new sensing protocols, improving them while we work on the challenges towards getting really molecules on the surface and the NV centers close there. So in the first half of my talk, I want to talk a little bit about our recent C13 carbon experiments and the challenges we encountered there. And then in the end, I want to give a little outlook on recent work towards really getting a functionalized surface. So as Fedor Jeleszko has provided a thorough introduction, I don't have to say anything about level structures and so on. Why I left that slide is just like for that image here on the right side, because what we do is we nanofabricate actually waveguide structures into the diamond to enhance collection efficiency and also to make it easier to address single NV centers which are sitting at the top of these pillars. At the same time, we have also the capability to deliver microwaves and RF pulses via a microcoil arrangement, and that, well, like that, allows us basically to interface both the NV center electron spin and the nuclear spins directly. So how can we do now with such a setup NMR spectroscopy? And for that, let's take a look how typical NMR experiments look like. And if we take a look at the most simplest experiment, the FID experiment, which was done for the first time actually pretty precisely 75 years ago by Erwin Hahn, then you can break up that experiment into a 3-step process, the NMR triad. And basically all modern NMR experiments you can break up into such a 3-step process. Initially, we need to create some polarization on our nuclear spins. In the classical NMR world, this is done just by Boltzmann polarization. Then you build up some coherences, which you let evolve in the manipulation phase and convert them basically into populations, which can then sensed in the detection phase, typically in conventional NMR by an inductive pickup coil with a free induction decay experiment. So the question is now, how do we have to translate this grammar of NMR experiments to the NV world? And this is our translation. And I would like to walk you a little bit through that sequence. You can immediately recognize again the triad process. We start with the polarization, but for the NV system here, we cannot rely actually on the Boltzmann polarization because it's way too small. So what we do is we use hyperpolarization techniques, essentially transferring the polarization from the NV center to the nuclear spins. And by that, ending up at the end with a nuclear spin system, which is nearly fully polarized. I don't have the time to go into details, but kind of the important thing is afterwards you have a spin system which is out of its thermal equilibrium value, and nearly 80%, 90% of the nuclear spins are actually on average polarized. Then we are in the manipulation phase, which is for the FID experiment, the most simplest experiment, rather boring. It is just a resonant pi-half pulse, which we apply directly via a microcoil onto the nuclear spins. And then for the detection now, we have somehow to sample the precession of the nuclear spins, which we initiated during the manipulation phase. And the interesting question is now, how can we do that actually efficiently? Because in terms of experimental time, this polarization step is rather expensive. And so you don't want to acquire just one time point per initial polarization step. And so our suggestion for that is actually to use sequential weak measurements. And by that, the idea is that you basically not read out the nuclear spin state completely with each readout, but only rather partially. And by that also, you only partially collapse the nuclear spin function. And if you only partially collapse the nuclear wave function, then in the end, you can read out multiple times. And so how does that sequence work? Well, in essence, it is this well-known AC magnetometry sequence. We apply in the beginning a pi-half pulse, then there follows a train of pi pulses, and at the end we apply again a pi-half pulse, but crucially now with a phase difference of 90 degrees. And the interpulse spacing, this 2 tau here, we match actually to the Larmor precession of the nuclear spins. And the idea of the sequential weak measurements now is that this time t beta, so the number of pi pulses we apply, actually defines the measurement strength. How strongly do we entangle our meter qubit, the NV center, with the nuclear spin system? And if we do that not in a fully projective manner, then afterwards, after such a readout, we still have preserved some coherence on the nuclear spin system, and we can repeat this sequence over and over. So how do the measurements results look like? Well, let's take first a look really for a single nuclear spin, which we addressed. And we see that we can actually see the precession of the nuclear spin. So we see kind of the FID decay of one single nuclear spin. And if we now decrease the measurement strength, well, then we get less signal. But at the same time, also our lines get narrower because we have less measurement-induced decoherence. If we do the opposite and go for stronger measurement strength, then we get more signal, but at the same time also our lines start to become wider. And this is because, yeah, we just like collapse the nuclear wave function more and more. And yeah, so going for weak measurements, we sacrifice some signal, but at the same time we gain more coherence, and the scalings are kind of gracious to us. That's why this technique actually helps us. And so in contrast to conventional MR, I want to point out here in this scheme where we are in the quantum limit, actually the measurement process itself contributes to the decoherence of the signal. It's not only the intrinsic line width of the nuclear spins. So the question is now, what happens if we're not looking at one single nuclear spin, but really at the whole environment of the C13 spins? Well, then we obtain a time trace signal which looks a little bit crowded. But if you do the Fourier transform then you get a little bit closer to the truth. So we observe one very strong peak at exactly at the Larmor frequency that is expected. This is coming from the most distant nuclear spins, and it's surrounded by a satellite, peaks from nuclear spins which are closer to the NV center, C13s. And now the question is, how can we actually image with that? Well, we need to ensure that we somehow encode the spatial information into the spectrum. And in classical MRI in the clinics, this is done using gradient fields. And we can actually rely on the gradient of the NV center dipole moment itself. And if you take a look at the complex spectrum, so not at the power spectrum, but at the complex variant of it, and you look at the phase, then you have in such a spectrum already encoded 2 of the 3 spatial variables. But to obtain the full 3D position, you actually need to do a sequence of weak measurements where you tune basically that T beta time, the time which defines you the measurement strength. And by that, you can scan the whole environment of the NV center, around the NV center. Why is it like that? Well, if you look at the acquisition profile of this weak measurement sequence, then it's basically a hollow sphere. In the center, you decohere the nuclear spins very fastly because your measurement strength is strong, and at the outside, well, you're not sensitive. And by now increasing the measurement strength, you basically let that hollow sphere grow, and by that you can systematically scan the environment around your NV center. So what we end up in the end is like a 2D experiment, like where we acquire a full series of such weak measurement traces, and those we can then fit into minimization and actually determine the nuclear spin positions with it. And in that case, we were able to determine the position of roughly 30 nuclear spins, C13 spins, around the NV center inside the diamond. So yes, we have kind of a way to image around. The question is now, this is all a toy model. What happens if you want to go towards the surface? And I want to spend a little time now on telling you a little bit more about, well, what are the challenges if you go towards the surface? And the problem with NV centers is if you bring them close to the surface, then they get somehow unstable. Like mainly they are plagued by charge instabilities. And of course, it's unfortunately necessary that you bring them to the surface because you want to send something from outside the diamond. At the same time, you wish to preserve all the good properties of the bulk NVs, and that's the dilemma in which you are, because the surface NVs, surface near NVs are plagued by a variety of things like magnetic surface noise, charge instability, the surface roughness, and so on. So what can we actually do to mediate that? Well, first of all, you should try to prepare an as crystalline surface as possible, because that reduces already the magnetic surface noise. And then what we are now using is like an oxygen treatment, where we basically bring the diamond into a hot oxygen environment, and that etches off all the graphitic carbon, and also it terminates the surface with oxygen, which is appropriate because of its positive electron affinity. And if you look at a variety of parameters, essentially doing EPR spectroscopy on the NV center, then you see that you increase them and improve them. That is the optical contrast, but also the coherence times that you measure on the NV center. So now we have them a little bit more stable. How can we now actually bring molecules to the surface? Well, we chemically modify this oxygen terminated surface by direct salinization. And for the results I'm sharing today, we attached actually amine labeled silanes to show the general stability of that approach, because like that, you can in the end attach any molecule you want with hydroxysuccinamide ester labeled target molecules. And here in this case, we just attached a terminal CF3 group. And maybe one word also on like complementary diagnostical tools we have available. This is X-ray photoelectron spectroscopy, which is actually a very nice and complementary technique that allows us to track the whole production process and the layer formation, the layer homogeneity, and so on. We can, for example, confirm that we have indeed fluorine there available, but also it's way more sensitive that you can see that you see actually the changing of the nitrogen binding state after attaching the terminal CF3 group. And since time is running up a little bit, I want to just answer the most interesting question. Can we actually see the fluorine also with the NV center? And yes, indeed we can. This is a spectrum which we acquired with dynamically decoupling spectroscopy, which Fedor Jeleshko already introduced you to. Unfortunately, the signal is a little bit weak because we are rather deep in the diamond. But nonetheless, we can see the fluorine as well as the proton signal, which is just from ubiquitous protons you have always on your sample and on the surface. And yeah, with that, I think I want to conclude. Just let me thank quickly all the NV NMR team at the ETH Zürich and you for your attention. And now I'm happy to answer your questions.
Thank you very much, Konstantin. So is there any question?
No, this is just like noise spectroscopy. Yeah. Yeah. Mm-hmm. Yes, that's true. But in the end, if you go to the weak measurement protocol, kind of your frequency resolution in the end is not determined by the length of that weak measurement block. It is rather determined by the total number of weak measurement blocks you apply, because this is essentially like a classical sampling of the signal you're applying, and that the total sampling time, that is what defines your resolution that you achieve in the spectrum. The width of the length of one individual weak measurement block, like how many pi pulses you apply, that defines your measurement strength. And yes, also the bandwidth, like the dynamic, like the whole bandwidth from which you would gain signal with that method. But it's not the line width of the NMR signal that is influenced by that filter function here. And kind of the also nice thing is you get independent somehow of the relaxation times of the NV center, because you reinitialize after each measurement the NV center, and by that you're not limited anymore to the sensor coherence time. Yeah. Typically, those measurements were done at 200 millitesla. So small fields for the NMR guys, large fields for us, but yeah. Oh, that is not yet fully understood from us, but I'll think it's just like, I mean, you have a spin diffusion for sure. If you're looking at a macroscopic volume around above your NV center, I mean, it's also not the most quiet environment if you have like nuclear dipole moments which are and dipolar interactions which are basically a powder average on the surface. So it's like for sure the lines will be broad, and they are broad like a couple tens of kilohertz. Yes. Mm-hmm. Yeah, I mean, that is kind of I mean, it's really by direct salinization that you expose it to the vapor of the salins, and then they stick.
Any more question? Okay, thank you very much, Konstantin, again for such a nice talk. So our next student talk will be given by Elena Redchenko from IST Austria, Klosterneuburg. Is it? Okay, yeah. You can hear me fine, yeah? Nice. So I know it's a last talk. I'll try to keep it simple and short. I would like to start with thank to organizers for choosing my talk, and thank to my amazing theoretical support. It's Alexander Shakinsky and Alexander Podubny from Institute in St. Petersburg. So I will talk again a bit off topic. It's going to be about superconducting qubits and creating non-reciprocal devices with the pair of them. So let me start with introducing non-reciprocity. First of all, reciprocity. It's actually a fundamental concept based on PT symmetry or T symmetry, which allows us to predict the behavior of complex systems. But in several cases, it's really beneficial to break it. And create several devices, for example, isolators to prevent backscattering to lasers, or in our superconducting qubit setups, we're often using several circulators, which helps to protect our states of cavity and superconducting qubits from the thermal noise. And also probably it might be interesting for some of you, non-reciprocal devices, actually non-reciprocal sensors might be much more efficient in detection than reciprocal one. And it's been shown before, but there is like one of the recent theoretical papers which shows that actually it can exceed the fundamental limit which limits its reciprocal sensors. So how people usually create those non-reciprocal devices? One of the most classical ways is using magnetic materials or like big magnets. So here is like a classical Faraday isolator circulator, but the downside of it is, first of all, big magnetic fields, which is not really compatible with superconducting qubits. And it's also bulky, so it's difficult to implement it, like if you want to create a big setup. Then you can use some nonlinear effects. And here is one work done also with 2 superconducting qubits in 3D waveguide, which is nice. Now it's compatible with our superconducting devices, but again, it's 3D waveguide, so it can't be implemented on chip, like if you want to create a huge superconducting quantum computer. And it also has some limitation in like frequency and possible applications. In optical domain, people often use like some stimulated Brillouin scattering. I think I've also seen some other type of scattering stimulated, but it's mostly like optical domain measurements, and we are working in microwave domain. And there is another way to use driven mechanical system. It's actually also work from our group. Here, the device allows to switch between circulators and oscillator regime, and it uses the mechanics coupled to the microwave resonators. The downside of it, it's difficult to fabricate. So let's see what I propose, actually, what the theory collaboration proposed. So we use motion-induced directionality. So in my system, there are only 2 superconducting qubits positioned in a waveguide. So that's like 1 and 2. And I need really specific distance between them, which is equal to lambda quarter. And this is because the photon which will be scattered from the second or the first qubit will experience some phase delay. And by modulating the phase with which I will basically shake the frequency of my qubit, I can match the phase delay such that the scattered light will experience either constructive or destructive interference. So basically, I can either kill the light which will be scattered backward or forward. And in my, like for this distance, if I send the tone to my waveguide and modulate 2 qubits in phase, I will only have a forward scattering, and if they are modulated out of phase, I will only have a backward scattering. So this is how device actually look like. This is an optical image of the sample. I have 2 superconducting qubits, which are transmon qubits. You've heard about them from Larissa earlier today, and they're capacitively coupled to the waveguide. And they have a way to be tuned in frequency by applying current here on chip to this like little Josephson junction squid. It's 2 Josephson junctions in parallel, which creates a squid loop. And by trapping different fluxes, you can change the frequency of the qubit. So if I now apply a constant current, I can just like constantly offset the frequency of the qubit. If I now, on the other hand, apply some oscillating current, for example, sinusoidal wave, I can actually periodically change the frequency of the qubit. And this is exactly what I'm doing. But again, I designed the sample such that the lambda 4 frequency is going to be around 6 gigahertz. But in experiment, you have to find it and prove that it's actually at this frequency. So what I've done is measure reflection, because in when the qubits have the quarter wavelengths between each other, they have a construct like this coherent interaction. So you can see an anti-crossing in reflection, and it's quite visible here. The intensity of reflected light extremely dropped down, but you can see those like 2 branches of this like anti-crossing. So as soon as I proven that like, okay, this is the frequency I want to work around, I need to now characterize the qubits. And I'm going to work with qubits at single photon regime. Qubits at single photon regime, there is no difference between the qubit and the resonator. It's basically same thing. I could actually, if I had a mean of like shaking the resonators in frequency so fast, I could do it with resonators as well. For the directional scattering, you don't really need the quantum nature of the qubit. So I characterize the qubits one by one at this frequency. From the depths and the widths, I can find the relaxation and dephasing rates, and they're here. And the next logical step is I have to check how my qubit will look like and behave if I modulate the frequency. So when you modulate the frequency of the qubit instead of a single dip, now the transmission described by the Bessel function, so you start seeing some sidebands, like stocks and anti-stock sidebands, and then higher harmonics of the sidebands. And by increasing the amplitude of the modulation, you can see that the sidebands becomes more pronounced, and actually the central peak, which was like the qubit frequency, gets shallower. And the amplitude here is in frequency units. And what I'm applying is actually in the current, like in ampere. So this measurement also helped me to kind of estimate the relation between the currents I'm applying and the frequency I got, like the modulation strengths. So that then next is like I fixed the modulation amplitude and I sweep the modulation frequency. So on this plot, you can see nice transition between strong modulation regime, where you mostly see side bands, to the weak modulation regime, where there is like a central dip and then small side bands. And as I said before, for my work, I don't really need a quantum nature of the qubit, but it's nice to sometimes show that there is actually something quantum about modulated qubit. So for this, I measured resonant fluorescence emissions in coherent, basically in coherent scattering pattern. If you ever heard about Molo triplet, so basically it's like the most basic measurement to show that you have a quantum two-level system. You apply the drive on your system, and then you see a triplet, which is basically would be like a cutout somewhere here. Like you see the main peak, which corresponds to the position of the qubit, and then like those side bands, which are exactly spaced as the Rabi frequency, and this is like a strength of your drive. So for these measurements, I actually turned on the modulation, and I was changing the modulation frequency with a fixed amplitude of modulation. And what I see that my Molo triplet becomes like a double Molo triplet. So the modulation of the frequency of the qubit, I actually also like have some quantum effect on the system. Although it's not the main thing, but it's nice to see that there is also something quantum in it. Okay, so let me now go to the main part of the talk, and it's directional scattering. As I said before, the directionality comes from the interference. So on those plots, I'm measuring, again, resonant fluorescence. And here you have to focus on the sidebands, because sidebands is exactly the thing which I'm actually doing directional scattering of. Like I'm mostly focusing on the sidebands. The central peak is a Rayleigh peak. It's just a coherent peak, which I send. So if I do modulation and phase, as I said, the light which is scattered from the first qubit forward and the second qubit forward, then those lights interfere constructively. So I see some sidebands here, and everything goes through. Now, if I turn on out of phase modulation for the second qubit, I basically flip the sign of the light scattered from the second qubit, and now there is a destructive interference, and you see nothing, like you see zero sidebands here. You can do the same for the backscattering. So if it's out of phase modulation, I finally start seeing some sidebands. And here in principle, I should see none, but experiment is not perfect. So I see some small sidebands. It's not a full suppression, but it's smaller than for the forward scattering. So this is like a main result, but you can do some more interesting thing. Like it's just two possible phase differences between the modulation tones, and I can actually slowly like sweep it over all 2 pi range and measure one of the sidebands coherently. So I basically focus on the stock sidebands. So I put my measurement tone, whatever frequency I have detuned from my excitation tone, and I measure it over like the full 2 pi phase change. And what we see here, besides those regimes where I have only scattering backward or forward, I also can find the regime in which I basically scatter symmetrically in both directions. So actually the system can be not only like isolator or like isolator to, whoa, it's vibrating. Okay, so it can not only isolate in like specific direction, but you can actually scatter it symmetrically. So you can switch between different regimes. And what is nice about it, like, first of all, there is a nice agreement with the theory predicted. And secondly, I can actually change the suppression strengths by just changing the amplitude, like going in the stronger modulation regime. So it's like tunable isolator. I firstly can choose the frequency. Okay, probably I actually have it listed in conclusions. So first of all, I can choose the frequency. I'm working with the sideband, so it's purely depends on the frequency of the modulation. If I choose the frequency of modulation to be higher, I can go and like work with sidebands which are further from the qubits. So this is like one aspect of the tunability. Secondly, again, as I said, you can either scatter backward or forward. You can switch direction. You can choose it by just choosing different phase difference between modulation tones. You can choose the bandwidth of the scatter light. This is although you can't do in situ. This you can only do if you fabricate new sample with like stronger coupling, but still like also tunable parameter. And you can also change the suppression strength. So you can create a stronger isolator, like weaker one. Maybe you have an application for that by just changing the modulation amplitude. And such a device could be used for like creating topologically protected states in the superconducting quantum computers, or like using some, like creating some chiral networks. And with that, I want to thank you for your attention.
Thank you very much, Elena. Do you have any question? So I have a very basic question. So what do you mean by this forward and backward scattering? Like, how do you define?
Oh, so I send light from one side, and then it either goes back or like through. So it's really simple because it's the waveguide is basically one dimensional. So you have only one direction. So it's either goes backward or forward. And I can measure simultaneously both of the directions scattered, and I can also send light simultaneously in both directions. So it's actually like two-port, like nice two-port system, which you can measure at the same time in like all possible ways. Yeah.
Okay. Thank you.
Thank you.
Okay, we wanted to take the group photo, but our photographer Vito said it's not a good time to get the photo because of the light. So we will do it tomorrow after the first lecture, because it's apparently better. I think it's now if we stand there, we all look like this in the picture. So it's not the best. And Timo, are you here tomorrow after Philippe talks, after the first lecture, like at 10:30? Oh, you're okay. Cool. So for today we don't have anything else, but we will have beer. So we don't encourage you to stay at the ATI. You can go and enjoy Vienna and just go around, but there is beer, so we want to have.